In this video, we will talk about how to calculate area with regards to polar coordinates and polar equations, because it's done a little bit differently, and it's even a little bit different to parametric form. If you remember parametric form, we talked about a little bit ago, but essentially there was the formula g times f prime of t with respect to t. If you integrate across the parameter, this will give you the area under the curve, assuming you got to be careful about the directionality and things with loops in terms of getting negative versus positive answers. But at the end of the day, it works roughly due to the connection between parametric equations and those of rectangular ones. However, with polar equations, you could apply that approach, but not even like I wanted to show you just basically how disgusting an integral would be if you thought about it in a rectangular sense, which is why we just basically abandon rectangular idea of area and do it completely differently. But let's say we were to look at it in a parametric sense, as we talked about in the last video. You can always change any polar equation to parametric form. And if we're thinking about the area in a rectangular sense, we'd have the integral of g of t times f prime of t with respect to t, and integrating across from alpha to beta, whatever the parameters are for the boundaries of the area with respect to the parametric equation that we're looking at. But basically, this would be f, and this would be g for the parametric equation of theta. And obviously I could just change these to theta, but basically I would have this one times the derivative of this one, and what that would amount to would be a very, very, very disgusting integral. I would have f of theta times sine of theta times the derivative of this, which would be first e second plus second e first. It's going to involve a lot of it's going to be the function times sines and cosines. It's going to be a big, huge mess. And again, it can be done using a calculator. Would be probably the more trying to do it like by hand is very disgusting. There's a way more elegant approach that is a lot simpler and a lot more meaningfully useful a lot of the time if we wanted to do area regions using polar coordinates instead. And it all begins with what's called the sector area formula, because rectangles are very convenient for finding area under rectangular coordinates. Circular sections of area are more convenient with polar curves because they're very circular in nature. And if you recall, the area of a circular sector is given by the formula 1/2 r squared theta. Because if we're talking about the area of an entire circle, the area of an entire circle is always given by pi r squared. Where let's say we wanted to segment this up into a particular part of the curve, basically, and let's say that this theta was an angle in radians. Basically, we'd want to multiply by the appropriate size of that sector with regard to the entire unit circle. And since one full circle has a circumference of 2 pi, 2 pi r, but thinking about it in terms of just the angle, this sector would be this appropriate amount of the fraction of the entire circle if given in radian mode. So if you're not quite following what I mean, let's say that this sector was exactly 90 degrees or pi over 2 radians. Notice if I plug in pi over 2 here, what I would get is pi over 2 divided by 2 pi. Pi's would cancel and I would get 1/4. And if I'm talking about a sector of 90 degrees, it would be exactly 1/4 of the circle. So essentially what this will do is will tell you how much of the circle is this. And essentially if I multiply pi theta over 2 pi times pi r squared, that would give me the sector area formula. So if I need to multiply those together, and the pi would of course cancel, I would get theta r squared over 2, and that is why so I'm just trying to explain why this sector area formula makes sense. This would give you the appropriate area of a circular sector. An important thing to remember is theta must be in radians. You can't plug in degrees in this formula. It will be total. It will make no sense. Because again, radians are unitless, degrees are unitary, and so that is a problem. Anyways, why do I bring this up at all? Well, basically, let's say we wanted to calculate the region underneath a polar curve given by the formula r as a function of theta instead of, a rectangular equation. Instead of considering the area underneath the curve, like typically how we think about area in calc, like especially in calc 1, is we connect it down to the x-axis, because we can, use our fundamental theorem of calculus, assuming the continuity of the function, y as a function of x, to calculate the area of the curve. But my point is, trying to do that type of area what I was trying to say earlier is that's very, very horrible, and it's going to involve a lot of sucky math and a really, really terrible integral. So the more elegant approach is, instead of looking at the area connected to the x-axis, what if we connect those two endpoints of the curve that we're concerned about to the origin instead? Because that's how polar coordinates really work. They work by looking at the radius r as a function of theta from that point to the origin instead. So it's a more sensible approach because that's just how polar coordinates operate. And so basically the question would be, well, what about this region? How would I calculate the area of this region instead? And if we kind of work analogously to the fundamental theorem of calculus, we could imagine breaking this region up into subintervals or subsections. So say I imagine taking this and kind of chopping it up into 5 or 6 equal pieces based on theta. So let's say that this was a 60-degree angle, and we broke that into, say, angles of 10 degrees each. Basically, I'm looking at little slices where each of those, kind of like a slice of pizza, where each of those pizza slices is 10 degrees. And if I add up all of the pizza slices, those 6 pizza slices give me a full 60-degree sweep of that region. And what I could then think about is, well, what's the approximated area? Just like with a Riemann sum, I could build a Riemann sum and say, well, if I wanted to know what is this area plus this area plus this area, and add up those 6 components of area, that would give me an approximation to the area. And that's exactly what this formula right here says, is the approximate area of an ith subregion. So where I is just an arbitrary index for, let's say this stands for I is 1, 2, 3, 4, 5, 6. Or again, there's a graph over here that is showing this that's directly from our textbook. And it looks like they've used more like 10 subregions, or I didn't actually count, but however many, doesn't matter. But the area of each of those subregions is approximated by 1/2 f function of theta squared, or r squared, times d theta. And if you're thinking about, okay, what does all this mean? Well, d theta would just be the change in theta, which is just basically, if we think about a sector area formula, that would be our theta parameter itself. And if we take that and multiply by 1/2 and multiply by r squared, notice that r squared can be approximated because this value is that of the function, and the radius, well, we could use either the left subinterval or the right subinterval in order to do this approximation, or we could just use an arbitrary point. Remember that that's what the star means inside of the function itself. It's basically an arbitrary value or any point within the subinterval. But essentially all this is saying is that the area of each of these ith subintervals is approximated by 1/2 r squared theta. The radius of each sector, because notice those are, my point is each of those are sectors, and we could approximate them by a circle. It's kind of like how with a rectangular equation, right, how we built our fundamental theorem is, well, we don't know exactly how much the area is of all of those pieces underneath the curve, but we could just turn them into rectangles. And that's why we take y dx, or y delta x, right? The sum of each of those y times delta x values, or f, it's why we can integrate a function with respect to x, and this will give us the area under the curve, or not the area attached to the x-axis is a better way of saying that. But basically, if we adjust our formula a little bit, we can figure out the area of all of those. And the area of the entire thing is approximated by adding up all of those n subintervals. And essentially, if we, instead of just taking n subintervals, let's imagine that we could do 100 or 1,000 of those, or if we could go towards infinity, like if we could take an infinite number of those subintervals. Again, as we apply more and more of those subintervals, we become more accurate. And so, sort of like, I like to use the analogy of thinking about it as threads underneath the x-axis, right? If I want to find the perfect area under the curve, instead of taking, say, 10 rectangles, I want to take 1,000,000 of them, and if I add up 1,000,000 little segments of area, that will give me the precise area under the curve if I could literally do it towards infinity. And similarly, if I could take an infinite number of subintervals, or how I kind of imagine is, say I could take literally infinity of these, right, and add up an infinite number of these little strands, each with infinitesimal width. If I continue adding up all of these things, and I could do that all the way to infinity, or 1,000,000 of them, that would give me an exact area under the curve. So the area is approximated by n subregions, but if I could take an infinite number of subregions, what I would get is the exact area under the curve. So this would be an expression for the exact area sorry, not under the curve, but essentially attached to the origin is a way you could say it if you're trying to describe what is this subregion doing. And of course, well, as we know, all of this is what the integral symbol means. If we change this to d theta and we change all of that to the delta theta to d theta, we have our calculus representation of what an integral means. And this is, again, by the fundamental theorem. And so to try to summarize our results here, essentially we can find the area, the precise area under the curve, by using an integral to do that. It's just we can't just integrate our function of theta. We have to integrate 1/2 f the function of theta squared times d theta, because essentially we're not looking at rectangles, we're looking at sector areas, and the formula for a sector is a little bit more complicated. It's 1/2 r squared theta instead of the area of a rectangle is xy. And that's kind of why we have integral of y dx is the area, the rectangular area underneath a rectangular curve. But a sector area is given, by a more elaborate formula, and that would be r squared, 1/2 r squared d theta. Because again, the area of a circular sector is 1/2 r squared theta, and to integrate a more complex polar curve, we need to integrate this instead. And so essentially this gives us the formula for the area of a polar region. And it's just different. But at the end of the day, it's not nearly as complex as trying to do it the way I was saying before. So let's do a quick example. So example number 1 says, find the area within r is equal to theta, which is the equation of a spiral, which is sometimes nicknamed Archimedes, because there are a lot of different spirals in math, but it's one of the most basic ones, which basically says, well, if I start at 0, thinking about the relationship between r and theta if it was in polar form, notice this is very different from the equation x is equal to y, which would just be that of a 45-degree line. But it's sort of like if I take a 45-degree line and start rotating it, that's essentially what this would give instead. So, well, one obvious is, 0, 0 is still going to be a point. The origin will still be a point on the polar curve. But let's say I want to change theta to pi over 4. Notice that as I move, basically as I'm rotating, it's moving around the x-axis. And then, by the time I get to pi over 2, I'm at pi over 2, pi over pi. Obviously, the equation is it's equating r and theta. So both of them will be equal. But basically, as theta is spinning, our distance from the origin is moving at the same rate. And you can kind of imagine this polar curve as, say you have an ant on a spinning record, and the ant is walking away from the center. Basically, this curve could represent the position of an ant, which is moving at a constant speed as it spins on a record. And you can see that polar curves can be very useful for spinning objects or rotational objects, very, very important in a lot of fields like engineering and physics and music and so forth. But anyways, so the example says, well, let's find the area within Archimedes' spiral for theta goes from 0 to pi over 2. So if we're looking at 0 to pi over 2, basically we'd be thinking about this is the point 0 and pi over 2 is up here. So if I think about enclosing that and attaching it to the origin, what the area will be that's kind of enclosed by that would be that kind of chunk, and it would be shaded like that. I'm not thinking about the area connected on the x-axis. It's done very differently. If I connect the points to the origin, basically you connect both of your thetas to the origin to find the region, and basically that's what I did. And since the first point was just the origin, it's all of that enclosed. It's essentially in quadrant 1, and that's kind of, if I'm thinking about theta as how it's being enclosed from 0 to pi over 2, it's the area within quadrant 1 underneath our but it's not underneath in terms of connect to the x-axis, if you see what I mean. It's just there's a little bit of a different thinking in terms of how we represent that region. But basically, if we wanted to do that, well, again, we could use the formula as it is in your packet, 1/2 r squared d theta, or 1/2 f theta squared instead. And since r is just theta, what we'd have, again, we want our integral in terms of theta. We'd have 1/2 r squared, and r squared, since r is just equal to theta, we would just plug it in for f of theta is just theta, so theta squared d theta. And the area under this is actually quite simple, because this formula, this polar equation is just theta. It's a pretty simple algebraic relationship. And as we know, the integral of theta squared by power rule is theta cubed over 3. So we'd have theta cubed over 3 times 2 is 6, and that would be our general antiderivative of this function. And since we're integrating from 0 to pi over 2, basically the boundaries on a polar curve, again, since theta, our differential is theta, our boundaries of integration also need to be theta, and they need to match that. So basically everything needs to be theta in order to solve this integral. And our boundaries of integration, basically we need to plug in pi over 2 to 0 into our antiderivative to solve this region of area. And, obviously 0 is going to give us 0, but plugging in pi over 2 would give us, well, pi over 2 cubed over 6 is going to be whatever this area will be. And, we'd have as well pi cubed, of course, and 2 cubed is 8, and 8 times 6 is 48. So what we end up with is a precise area of pi cubed over 48. And if I was, I could also come up with a numerical approximation. Let's go ahead and do that, because that's always useful to, whenever I'm calculating regions of area, I always recommend to think about, does that answer make sense? Again, this would be in square units. We don't know if this is in inches or whatever, but it is a region of area, but we're coming up with an answer of about 0.65 square units as the amount of area. And if we think about kind of common sense, does that make sense? Well, notice that if I kind of enclose this with a rectangle, it would be an area of about, 1.5 by 1. So that would be about 1.5 square units. And it does appear as though the spiral encloses not even about half of that. So 0.65 seems about right just from my approximation to how much that should be. But of course, assuming I did the math correctly, it will give us a precise answer, and who needs approximation when you can do something exactly. And similarly, say I wanted to do the entire spiral. Say I wanted to go all the way from the origin all the way to 2 pi, and I kind of imagine this looks sort of like a seashell. And if you wondered, the pattern of how shells on, sea creatures grow, they grow in spirals. There's a lot of applications to these sorts of curves in nature. Now, Archimedes spiral is not, there's other types of spirals, as I mentioned. Archimedes spiral is not the proper spiral for a lot of biological patterns, but it is useful in a lot of areas, as I was trying to say with the ant walk, for something spinning a record or so forth. But if I want to find that area, all I need to do is adjust my formula to 1/2 r squared theta instead of from 0 to pi over 2, just from 0 to 2 pi, and that would give me a full circle or a full spin of that spiral. And the area would enclose would be not just that, but it would include all 4 quadrants going all the way around. And again, it's always going to be attached to the origin. So it's kind of like if I'm trying to find the area of this shell-looking shape, it would give me all of that. That's, essentially how it would be in polar form. It would give kind of a full sweep, one full sweep of the pattern. And of course, I could, I already know the antiderivative because it's just by power rule. But it would be theta cubed over 6. Theta cubed over 6 was the general antiderivative and evaluated at 2 pi instead. So, 2 pi to the third would be 8 pi cubed over 6. It's going to be a much larger. Of course, I could reduce by 2 if I wanted and get a precise value for the area of that region. And again, it's by the fundamental theorem. It's just we've changed the fundamental theorem a little bit to properly work in polar coordinates. And again, the way that we think about area just has to be done a little differently if we're going to use that formula. But most examples of polar curves, you want to think about it as attached to the origin, because that's kind of the original line of thinking of how it works to begin with. And, if I went ahead and calculated that as an approximated value, we could think about, okay, does this answer actually make sense before we move on with our lives? But we get about 41 square units of area here. And thinking about this, well, this is a much larger portion. And, just thinking about this part on the bottom, it's about 9 wide and 5 tall. So like 9 by 5 is about 35. And it's not quite enclosing that completely, but it's somewhere around 30 square units. And this is about 10. You know, it makes approximate sense. And so we can make sure, you know, does this make sense based on what we think? Anyways, sorry this video has gotten a little bit long. In the next video, we will look at a couple more. And then, you know, we'll move into arc length as well soon.